Bessel's inequality. First of all, statement: let V be an Euclidean space, and beta 1, beta 2, dot beta n be an orthonormal set of V. Then for any vector alpha belongs to V, norm alpha square is greater than equals to c1 square plus c2 square plus dot cn square, where ci is the scalar component of alpha along beta I for I equals to 1 to dot n. Now proof. We have V is an Euclidean space, and beta 1, beta 2, dot beta n is an orthonormal set of V. Therefore, inner product of beta I, beta j has two possibilities: 0 if I not equals to j, and the second one is 1 if I equals to j. Also, Ci is the scalar component of alpha along beta I for I equals to 1 to dot n. That imply alpha equals to inner product of alpha comma beta I divided by inner product of beta I comma beta I, that is equals to inner product of beta alpha comma beta I for I equals to 1 to dot n. Now consider alpha minus c1 beta 1 minus c2 beta 2 minus dot minus cn beta n belongs in V. Now inner product of alpha minus c1 beta 1 minus c2 beta 2 minus dot cn beta n comma beta I equals to inner product of alpha comma beta I minus ci into inner product of beta I comma beta I, that is equals to ci minus ci equals to 0 for I equals to 1 n. For alpha minus c1 beta 1 minus c2 beta 2 minus dot cn beta n is orthogonal to c1 beta 1 plus c2 beta 2 plus dot cn beta n. Therefore, alpha equals to alpha minus c1 beta 1 minus c2 beta 2 minus dot minus cn beta n plus c1 beta 1 plus c2 beta 2 plus dot cn beta n equals to beta plus gamma, where beta equals to alpha minus c1 beta 1 minus c2 beta 2 minus dot minus cn beta n, and gamma equals to c1 beta 1 plus c2 beta 2 plus dot cn beta n. Here norm gamma square equals to inner product of gamma equals to c1 square plus c2 square plus dot cn square. Now by Pythagoras theorem Pythagoras theorem, we get what we get? Norm alpha square equals to norm beta plus gamma square equals to norm beta square plus norm gamma square, that is greater than equals to norm gamma square equals to c1 square plus c2 square plus dot 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 cn square. Hence norm alpha square is greater than equals to c1 square plus c2 square plus dot 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 cn square. Now Parseval's theorem. First of all, statement: let V be an Euclidean space and beta 1, beta 2 dot 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 beta n be an orthonormal basis of V. Then for any alpha belongs to V, we get what we get? Norm alpha square equals to c1 square plus c2 square plus dot 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 cn square, where ci is the scalar component. Now proof: we have V is an Euclidean space and beta 1, beta 2 dot 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 beta n is an orthonormal basis of V. Now let alpha belongs to V, then alpha equals to c1 beta 1 plus c2 beta 2 plus dot 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 cn beta n, where ci equals to alpha comma beta I, inner product of alpha comma beta I for I equals to 1 to dot 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 n. Therefore norm of alpha square equals to inner product of alpha comma alpha equals to c1 square plus c2 square plus dot 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 cn square.